Yesterday we defined a contact structure that appeared to be a contact manifold together with some distribution, which means at each point we have a subspace, vector subspace of a tangent space at this point, and this distribution is very non-integrable. We explained what does it mean that it is maximally non-integrable. We have seen examples of contact manifolds. The first and the simplest was just the cotangent bundle multiplied by real numbers. From the same class of examples was the first jet bundle of Möbius manifold, and from another class of examples was projectivized tangent bundle to any manifold we like, and especially if we take Q to be a two-sphere, then what we obtain is, as this projectivized cotangent bundle is isomorphism to S3, which is free sphere, and as a result we can construct a contact structure on a total space of the Hopf bundle, whatever it is. However, a Hopf bundle has habit of appearing out of a sudden in whatever mathematical geometrical theory you try to do. Then we described the contact manifold by means of contact forms, which appeared to be in many cases only locally defined. However, they are very useful, so we wanted to know how this maximal non-integrability is expressed in terms of contact forms, and it was just this condition that the volume form constructed out of a contact form is a volume form, so it is the top form, which is non-vanish. And then we also associated to the contact form the notion of rep vector field, which is defined by the conditions which are here. It is in the kernel of the differential of the contact form, and there is a normalization condition. And I said that this is and this rep vector field is a notion which is studied in general differential geometry. And there are many papers, and there is one important problem attached to it, which is called Weinstein conjecture. So this is for the research. And we have also defined, but we didn't explore much, the concept of a contact Hamiltonian vector field. And again, there are conditions which resemble a little bit a definition of the Hamiltonian vector field for the symplectic case. If we want the symplectic case, it would look like that. We have a Hamilton function on the symplectic manifold P. So P with symplectic function, with symplectic form, it is a symplectic manifold. The Hamiltonian vector field is a vector field on P, which is defined in such a way that if I contract it with the form, I get the differential of the Hamiltonian, and there are of course some sign conventions as usual. You can decide whether you contract on the first place or on the second. You can decide whether you take plus differential of the Hamiltonian or minus differential of the Hamiltonian. It depends on the applications and on the particular test, but essentially this is what it is. In physical terms, it associates to Hamiltonian, which is, in most cases is just the energy of the system. It depends on the positions and momenta. It associates a differential equation, which is Hamilton equations for phase trajectories. So So here we have a generalization of it to the realm of contact geometry. And as you can see, it is quite similar. So still there is a contraction with some 2 form. And this contraction is supposed to be the differential of the function. However, there is a correction coming from rep vector field. And since this form has a kernel, it is not symplectic because it is not non-degenerate. Therefore, this one condition is not enough. We have to have more, and here is the condition that fixes the scale of this vector. It says how long this vector is. This fixes the direction in a sense, and this fixes how long the vector at each point is. And there is the question, why so? I mean, those two conditions are they are similar to the symplectic case, but they are in some sense out of the blue. Why like that? And I will try to answer this question. I would like also to remind you that we had with this Hamiltonian vector field the concept of the Hamiltonian vector field, we had some problems. The first problem was the definition of the Hamiltonian vector field is local, so we don't have it as a rule on the whole contact manifold because the contact form is local, so the vector field also is local. And there is the relation between Hamiltonian vector fields and Hamiltonians is not that clear because contact forms are not uniquely defined. We observed that when we multiply a given contact form by a non-vanishing function, we obtain a contact form which is as good as the previous one. Therefore, we can take a Hamiltonian and produce a Hamiltonian vector field. Is it the same? Of course not. But how we determine this relation between Hamiltonians and Hamiltonian vector fields, we probably need some more tools to do that. And here another observation was, and we didn't do this calculation, it will appear in a moment, that Hamiltonian vector fields preserve the contact structure in the sense that if you calculate the flow of this Hamiltonian vector field, which is a bunch of trajectories, and when you move along this trajectory and you check how your distribution changes along this trajectory, the answer is it doesn't change. So this is the symmetry of contact distribution. Therefore, there should be a possibility to define those symmetries in a different way than by contact forms which are local and which are not preserved by Hamiltonian vector field. So now I'm going to introduce a notion which will help us in solving those three problems and will help us understanding how the origin of the formulae for contact Hamiltonian vector fields, and also the relation between Hamiltonians and Hamiltonian vector fields, and also it will allow us to define Hamiltonian contact vector fields without using the form explicitly, this contact form explicitly. Maybe I should also say at some point, maybe now is not a bad idea to do it, why I do study a contact geometry at all. For example, I mean, there are several reasons, but the two can be spelled out quite easily. It is a tool to describe dissipative systems. If you consider symplectic Hamiltonian mechanics, it is all about conservative systems, because the Hamiltonian is always constant on the trajectories of the Hamiltonian vector field, so the energy does not change along the phase trajectory. And if you want to add some dissipative force like friction, like some viscosity force or whatever, you need another tool. and this tool may be, for example, contact structure. And then deriving the equations using some geometric structure may help in a sense that even if your equation is too difficult to solve by hand, you can draw some conclusions about solutions using the fact that it came from some geometric structure. So this is one example. One reason why do we study contact geometry. The other reason is that it has something to do with geometric procedure of solving partial differential equations of order 1. And again, if you have a partial differential equation of order 1 such that the equation does not depend on the value of unknown function, so it involves only differential, then the problem is symplectic. And then you have a Hamilton-Jacobi theory. I will stop. Jacobi, not Jacobi. So then you have Hamilton-Jacobi theory. And if you progress to partial differential equations with when the value of the function is also important in the equation, so the equation depends on the value of the functions and on the first differential, then you have to use another version of Hamilton-Jacobi theory, which is by nature contact. Those of you who were taught some partial differential equation probably remember the method of characteristic in solving this equation. So this is precisely that. And this will be one of the examples of applications that I will probably present tomorrow. But today we are going purely geometrical, and we are trying to make sense of what is more natural, more flexible and easier tool to speak about contact geometry. And this tool is, as it is said here, a symplectic principal bundle. So what's that? So a symplectic principal bundle is a principal bundle with the group that acts on the fibers is a group of non-zero reals with multiplication. So the group is written here. You take the real numbers, you remove zeros, you remove zero. When you remove zero, then this set with usual multiplication becomes a group, and it has two components. Yeah, the positive numbers and negative numbers. And what I'm thinking of now is a principal bundle with this group acting, which means that I have two manifolds, P and M, and on this manifold the group is acting, and it is acting in such a way that the action is on the fibers. So if I have a projection here, so over one point I have a whole fiber which looks as R cross, so R without zero, and this lack of zero is here. There is this hole. Yeah. So the fiber looks like that. The difference between the fiber and the actual R cross is that I don't know what is the one. There is no neutral element here distinguished. So I can multiply elements by numbers, so I can move along this fiber by multiplying by numbers, but I don't have this distinguished number, I don't have this neutral element. So I can only add, I cannot multiply two elements with two elements of the fiber by themselves, but I can act with numbers. So this is the object I do need, and this object has more need to have more structure. So as I've written here, there is this total space, there is this manifold, the base manifold, and the difference of dimension because between those two manifolds is 1, because there is this one-dimensional fiber over every point of M. And there is the group acting, and this is the action. So this is the action, which means that this is the map like that. I take a number and an element of the total space of the bundle, and I, as I said, multiply it, and it should work as multiplication. So it means that when I first move by T and then move by S, so this is the same that I move by ST. So this is the condition for this map being an action. And I will also use simplified shortened notation. When I fix S, then I have just a map from P to P. Every point is multiplied by S. And this condition in terms of those shortened, in the shortened notation reads like that I compose those maps, it is the same as moving by the multiplication of the numbers. And this is not enough to have to recover contact geometry. Another element of the structure is the symplectic form. This bundle, this total space of the bundle, should carry a symplectic form, which means it is a two form which is non-degenerate and closed, and moreover there is a compatibility condition between the group acting and the form. This form should be homogeneous. So if I pull back the form by the multiplication, I get S times omega. And there is very natural example of such an object. I mean now only the form, not the whole thing. The examples of the whole thing will appear soon, but for you to see some example of homogeneous one form, it is just, let us take a manifold which is a cotangent bundle to some manifold. This is canonically a symplectic manifold, which in coordinates is written like that. Sorry, the position of indices is wrong. And on this bundle, there is group acting. Since there is a zero section here, yeah, it is not a group. No, maybe this is a group action. Okay, if I let us remove a zero section. We will have precisely the object as we want to be. So if we remove a zero section, there is R cross acting, and this form is homogeneous because I can multiply a covector by a number. So momentum can be multiplied by a number. And this map, if the momentum is non-zero, this is just the object as I presented. And I can calculate what happens when I multiply the momentum by the number, and I see that what I get is S dpi dqi, which means I exactly have S omega m. So using another language, I would say that since the canonical symplectic form is a linear object, so it behaves like that under multiplication by numbers. Okay, so summarizing, I have or even like that. I have a principal bundle with R cross group acting, and I have a symplectic manifold on the total space, which is homogeneous. And of course, now we know a little bit more about our total space. Since it is a symplectic manifold, it is of even dimension, which means that M is also always of odd dimension. And this shows us a little bit a link towards our our contact geometry. So now, and here I even have an example of such a thing. If I started to write this example before, so if I take a cotangent bundle, remove a zero section, and act by multiplication by numbers, what I get is precisely such an object, which is a bundle over projectivized tangent bundle. So we see that here we had our canonical contact structure. So the bundle will be over contact manifold. Okay, so let us now state the main theorem and then explain it. So the theorem says that contact manifolds and those objects, I mean symplectic principal bundles, are equivalent notions. It means that if I have a contact manifold, I can produce such a bundle out of the data that are associated with the contact manifold, and the other way around, if I have a symplectic principal bundle like that, I can produce a contact structure on the base on this bundle. And now we will be doing just that. Since from time to time some faces and people appear here, some professors, so this is another professor, Professor Grabowski with Tatra Mountains behind him, and this is the author of precisely this idea. Okay, so now let us show how contact structure, contact distribution defines such a complicated thing like principal symplectic bundle. So what we need, first of all, we need the total space of the bundle. And this total space of the bundle appeared already. This is the annihilator of the contact distribution. The annihilator of the contact distribution is a submanifold in T star M, so in one dimensional at each point. Since at each point C is one codimensional, it means that the annihilator is one dimensional. And to have a principal bundle, I have to remove the zero, as in the case of the group and as in the case of the principal of the projectivized bundle. It is this thing, it is a line bundle, so one-dimensional vector bundle. When I cut out the zero, it becomes a principal bundle with R cross acting. Okay, and the projection is, of course, the usual cotangent bundle projection restricted to what we have selected. And now I need the only thing really I need to point out is this symplectic form. No, because the action is there. This is the action by multiplication by numbers in the cotangent bundle, only restricted to this line or principal bundle lying within the cotangent bundle. So the proposition says that P is a symplectic submanifold of T star M. This means that if I restrict the canonical symplectic form to this subbundle, the C0 cross, I get another symplectic manifold of smaller dimension. For this, of course, I need P to be of even dimension, which it is, because I know that contact manifold is of odd dimension. I add one dimension in the fiber, then this is of even dimension. But now I need to restrict somehow the form. And I need to restrict the form, and I need to check that the restriction is non-degenerate again, and as the symplectic form is. Now, because the restriction will be automatically closed, because the original form is closed. So the only question is non-degeneracy. So we have to show that the restriction, which can be written as a pullback by the inclusion map, that this restriction is symplectic, which means that it is not degenerate because closed is obvious. And I will do it locally, because this property, I mean, if it is around each point, then it is everywhere. Locally, I will do it by means of a contact form. I choose a contact form on some subset of open subset of my contact manifold, and I defined, in some sense, a trivialization, a local trivialization of my principal bundle. So I take this open subset and I multiply it by the group, and I map it into the annihilator, just multiplying the local contact form by a number. So this is a very simple map. And using this map, I pull back the contact form, which I pull back the symplectic form that lives here. I pull it back on this manifold. So what I'm going to calculate is a pullback by this trivialization of the canonical symplectic form. This is what we'll be doing. So the calculations, how I pull back the contact form, the symplectic form. The symplectic form on cotangent bundle is not only closed but also exact. It means that omega m is a differential of the some one form which is called Liouville form, and which in coordinates, this Liouville form is PIDQI. This form has quite nice properties. So I pull back, then I use the fact that I can freely exchange the differential and the pullback. Then I use the actual form of my map, and then I use the property of the contact of the Liouville form. The Liouville form has this nice property that whenever I pull back the Liouville form by any one form, this one form is thought of as a map from the manifold to the contact bundle, to the cotangent bundle. So I pull a symplectic form from here, not symplectic, Liouville form from here to here. Then I always get alpha. This is the theorem, quite easy to show. So when I do that, I apply this here. So I pull back my Liouville form by this one form. This means that I recover the same one form, then I differentiate, and I got some formula for the pullback. And now my task is to show that this is a symplectic form. Here I have diffeomorphism. If I show that here I have a symplectic form, then it means that here I also have a symplectic form. So to show that it is non-degenerate, I can, for example, calculate the external power, external n+1 power. If it is a symplectic form, then this external power should be non-vanishing. So I calculate it. First of all, there is this component where I take the power of this part, and this vanishes because what I have a 2 form which is lifted. This is 2 form on the base on O, and this O has the dimension 2n+1, and the form here is 2n+2, which means that this is the order of the form is too much. Every such form is 0. Okay, so then the next component will be I take the exterior product to the power of n. I take this to the power of n, and I multiply once by this. There are several components like that. So I get s to the power n plus power n, sorry. S to the power n, and then the 2n plus 2 form is like that. This is 2n plus 1 form, which is non-vanishing because eta is contact, and this is also non-vanishing. When I multiply those two forms, I get something which is non-zero. Therefore, I have shown that my form is symplectic. And the last condition of this restriction being homogeneous is obvious because omega m is homogeneous, so the pullback is also homogeneous. So what I've done, I have shown that there is some principal symplectic bundle associated to the contact structure. It is just the annihilator with zero section removed and with canonical symplectic form restricted. And that's that. The remark we can skip. And then we go back. So now we take such a structure, symplectic principal bundle, and we try to recover the contact distribution on the base. And this is a little bit more complicated. What I have to do is first I have to calculate the action vector field. So here you see there is a picture about of the part of my principal bundle. It looks quite trivial because this is only a part of it. So there is some open subset on the base, and there are those one-dimensional fibers with a hole in the place when zero should be, but there isn't because it is a principal bundle, not a line bundle. I can act by numbers in the vertical direction along the fiber. And when I consider such a curve that maps a number to one particular point translated, multiplied by the number, I have a curve. I can take a tangent vector to a curve at s equal 1. This means that I exactly get a tangent vector which is attached at this particular point that was translated. Or if I really need to differentiate at 0 when defining vector fields or tangent vectors, I can always put e to the power of t here, and then I differentiate at 0, and the result is the same. So, and I can do it at each point, which means that I have a vector field, a vector at each point, and this vector field, it has a special property. This property is invariance. So when I move the whole picture by multiplying by a number, nothing changes. To see that it is really invariant, I can make a calculation which roughly goes like that, I take the curve that represents this vector and I move the whole curve. However, since this is an action, I can, of the abelian group, I can freely exchange the order. So this starts to look like that, and then I differentiate with respect to that, which means that I obtain again a vector like that, but attached at different points, and this point is the previous point translated. So I start with the vector, I use the tangent map, I obtain again a value of the same vector field. This means that this vector field is invariant. So now I look at the following picture. I take up my symplectic form, I contract it by a vector, and I get a one form naturally. If this was homogeneous and this was invariant, then this is also homogeneous. And I have a proposition. The one form I constructed is a primitive for my symplectic form. So it appears that in this case, always the symplectic form is exact. And I have also a formula for the primitive. So let us check that this is true. The fact that this is true comes from the fact that the form is homogeneous. If the form is homogeneous, this means that when I take a Lie derivative with respect to the vector field that encodes this action, that's my form becomes invariant with respect to the Lie derivative. And then I can apply the formula for the Lie derivative. So the Lie derivative consists of contracting with a vector field and then differentiating, and doing the thing with the other order. So first differentiating and then constructing. And since I started with the symplectic form, this is 0. And I obtained exactly what I wanted, that my symplectic form is a differential of the one form I have just defined. Okay, so where is this contact distribution? The contact distribution is the following. No, not yet. I will now, using this data, I will now construct a local contact form. So we will, I might define a distribution immediately, but then we will have problems with proving that this is contact. Which means that I will do it by stages. So first I will define a local contact form. How do I do it? I choose a local section of my principal bundle. So I choose an open subset here, and I take a smooth map such that to the one point in the base, I associate a one point in the fiber in such a way that this is smooth. So the image of this open subset is some kind of surface or something in the total space. This thing defines me a vertical coordinate, because I have a one-dimensional fiber, and I already said that this fiber very much resembles the group. So every fiber looks like R cross, but there is no neutral element distinguished. However, if I have a section, I have a neutral element distinguished. So I put this coordinate S equal 1 precisely here. And then from here I move by numbers, by multiplication, and I have a vertical coordinate. So a local section provides me with the local trivialization. So I may split a point in the bundle into a particular base element x, which is here, and a particular number, which is a value of the coordinate which is defined over the fiber. And this is the map. So I take this distinguished element and I move it by the coordinate, and I obtain element of the P. This is my local trivialization. If I have a vertical coordinate, this homogeneous coordinate, then I may write my vertical vector field that appears to be just d over ds, and I may and I may also transform my homogeneous one form into invariant one form, dividing it just by this vertical coordinate. If it is an invariant one form, it means that in fact it is a pullback by my projection here of some form which is defined on the base, and more precisely it is defined on the open subset from which I started with my section. And this appears to be, this eta here appears to be a local contact form. So let's check that this is really a local contact form. I have a proposition now for the proof. And this is like the previous calculation, but done, I mean, the calculation is the same, but the conclusions are different. Because previously, we have known that eta is a contact form, and we could draw the conclusion about some particular symplectic form that we constructed. And now it is the other way around. We know that we have at our disposal a symplectic form, and by knowing that it is symplectic, we will conclude that eta is contact. However, the calculation is really the same. So I again start with a pullback by my local trivialization of the symplectic form. I replace symplectic form by the differential of theta. Now it is not the canonical Liouville form as previously, but it is this primitive constructed by means of a vertical vector. But then, I mean, the formula is the same. I differentiate, but then I know that this is symplectic. So then I know that the certain power is non-vanishing. And since the differential of the vertical, or the differential of the coordinate is always non-vanishing one form, therefore this is also a non-vanishing, it means it is a contact form. Therefore, now I can take a kernel of this contact form on the open subset here and have a contact distribution on the open subset here, which is definitely not enough because I need to have it everywhere. So everywhere on M. So what I have to do, I have to check how it all behaves when I change the section. So here is the picture. I have two sections. Again, my piece of my principal bundle, one section, the second section. If I have two sections, I have two different vertical coordinates. And I can translate one to the another. The difference between 2 points in the same fiber is always by action by some number. So to pass from this section to this section, I may multiply elements on this section by some function, which will of course be a non-vanishing function, because even if those sections at some point are the same, then the value of this function is 1. Yeah, I have written it like that. I have drawn the picture like that. That it seems that this function is positive, but the green section could also be here below 0, say. So then it would mean that this function is negative, but non-vanishing. And the proposition says that if I take the kernel of two forms, one defined by use by section by the purple section and the other defined by use of the green section, the result will be the same. I mean, the kernel will be the same. So let us see how it looks like. So we have to compare those two forms. The non-primed form defined by sigma and primed form defined by eta. These forms come from dividing the actual geometric object living on the total space of the bundle. This one form, which is primitive for our symplectic form, we divide it by once by S and once by S prime, and we check what happens. So we need to know how S coordinate translates to S prime coordinates, and when we look closely, we see that it translates just by multiplication by this function that takes us from one section to the other. As a result, we see that eta from eta prime, that there is a difference between eta and eta prime by the multiplication by non-vanishing function. So it is 1 over f, but since f is non-vanishing, 1 over f is also non-vanishing. First, it can be written meaningfully, and it is also non-vanishing. So if I have a proportional one forms by non-vanishing function, I have the information that the kernels are the same. So taking local sections over open cover of my base manifold, I can construct the contact distribution everywhere on M. So I have finally shown that really starting from principal symplectic bundle, I can obtain contact manifold, and starting from contact manifold, I can obtain principal bundle. So whatever I do on contact manifold, I should be able to do meaningfully on this principal bundle. And this is the essence of this. This principal bundle is, from my point of view, better tool to define things on contact manifold. There is a short remark here that says that we should probably simplify we could probably simplify the construction of the contact distribution, just taking the kernel of theta and projecting it down to M. Now, because essentially it will be that what we obtained as a contact distribution. To see, for example, that the dimension is correct, we could think, okay, we have 2n plus 2 dimension of P. So P is of dimension 2n plus 2. So the kernel of one form will have dimension 2n plus 1. But definitely the vertical vector field belongs to the kernel. It's a section, this is a section of this kernel. And this vertical field projects to 0. So the rest of the distribution, of the projected distribution, will definitely have the dimension 2n, which is the correct dimension of the contact distribution on M. But proving that this is a contact distribution by means of just theta would be more difficult, therefore I preferred to do it patch by patch using local contact forms. And now we could think, okay, so this is a way, I mean, using local symplectic, using those symplectic principal bundle, it is a way to define contact distributions. We have seen it in this particular example, where there is a very natural symplectic structure on this came from T star Q with zero section removed, and this projects to the projectivized cotangent bundle. So this is probably the simplest way of defining this contact structure. We can then skip all those considerations in coordinates, building local contact forms and showing that by change of coordinates they properly translate into each other. We just see, okay, look, that's the principal symplectic bundle. So it gives the contact distribution on the base. But those things are not that obvious for other examples. So let us think about the other examples were up to now T star Q times R and the first jets. So both, in a sense, are particular instances of the space of first jets of line bundle. For technical reasons here, I take here dual line bundle, but this is only technical, and it comes from the fact that sometimes I will have to put cross somewhere and star somewhere, and it's better to avoid writing L star cross, yeah, because it gets confusing. So I decided to consider jets of the dual bundle, not of the original bundle, but I mean, conceptually it is the same. So we will try to find P for this particular example of the contact manifold, using some some things that we know, things like cotangent bundles, line bundles, dual bundles. So, of course, we know that this exists, and we know the abstract description, but we want to find it somehow to fill it. Okay. To do that, we should for a while explore the relations between line bundles and principal R-cross bundles. It is quite simple. So if I have a line bundle, which is one-dimensional vector bundle, every fiber here is a one-dimensional vector space. Then by removing zero section, I obtain precisely R-cross principal bundle, not symplectic. Symplectic will be later. This is just R-cross principal bundle, no additional structure. And if I don't want to put a cross and I want to put a star, I can consider a dual bundle. So at each point, I take a vector space which is dual to the original fiber that belongs to this point. Then I obtain a line bundle which is dual. And what we will be considering, jets of this thing, and we will try to find the proper P by using the tools that appeared here before. In particular, we will look at the cotangent bundle to this principal bundle. This is the thing. This is the P, but how to see it? First of all, we need to have an action of the numbers, yeah. So let us construct this action and let us do it in coordinates, because then we see what happens. So we have coordinates on the base. These are those QIs, and this is the coordinate in the fiber of the bundle. L cross, which means that T is always different from 0, and as QIs, they belong to Q. They are coordinates on Q. And the action written in coordinates means that I just multiply the second coordinate by S. Okay, so now I lift this action to the tangent bundle. So instead of moving points, I start moving tangent vectors. And in coordinates, it is again very simple. The tangent vector is in coordinates composed of the point when it is attached and coordinates of the tangent vector. And when I move this tangent vector, it means that I move the point as previously. And also, it happens that this coordinate is changed. This coordinate is not changed. This coordinate is changed. Okay. The tangent map. So this is just taking tangent map to this multiplication by numbers. Yeah. Since it is an isomorphism of line bundles, not line. It is an isomorphism of vector bundles, the tangent bundles, the two copies of tangent bundles, and this is the isomorphism. Then I can dualize it, fiber by fiber. It means that I obtain the action acting on the cotangent bundle. So here I have coordinates of the cotangent bundle, again a point, then a momentum, and then the bundle which is dual to the coordinate which is dual to that one. When I dualize, something a little bit nasty happens, because usually when you take dual map, the order changes and the dual map goes backwards. So on the base, it means that I essentially divide by S, and on this vertical direction, I multiply by S. So I don't like it. However, this is, after all, a covector. I mean, these are coordinates of a covector. So covector can be multiplied by number, and I will use it. First of all, instead of acting by S, I act by 1 over S. So here I multiply and here I divide. And then the result, I multiply result by number, so this is multiplied. So finally, I have defined my action. When I multiplied those two things by S, I get the action that multiplies here and multiplies here, and nothing changes here. What I defined is the cotangent lift of the action to the cotangent bundle. So I have the action here, I construct a lift, the same group acts on the cotangent bundle. And this is the action written in coordinates. So when I divide by this action, I already know how coordinates on the base look like. So these are invariant and these are invariant, so they survive this procedure of dividing. And these are not invariant, however, the ratio is invariant. So, so the orbit of the action will be characterized by the ratio of those two coordinates. And remember that t was non-zero, so I can divide by this. Okay, so this is in coordinates, but how to recognize what the base is? I have an action, so I have my cotangent bundle, I have an action, I have a symplectic structure because it is cotangent bundle, so it has symplectic structure, but I don't know what is the projection and what is the base. And it appears that the base is exactly the first jets of the dual bundle. And this is the last thing I'm going to explain today, because I am just approaching the end of my talk. So how to recognize the base bundle as being a jet bundle? So first of all, we should think of sections of the dual bundle as functions on the line bundle. So I have, oh, maybe this line bundle should be rather drawn on this side. So how the section of the dual bundle becomes a function on the line bundle? No, I just at each point take the covector, which is the value of the section, and I act as vectors, yeah? And I get a function which is essentially linear on the line, on fibers of the line bundle. But if zero section is removed, then this linearity becomes homogeneity, and to any section I can associate a function which is homogeneous. So now, what with the jets? If two sections have the same jets, so their images are tangent of the first order at a particular point, that means that those two sections differ by multiplication by function that has at this particular point value 1 and the differential 0. This says that those images are tangent. And then I check what happens on the dual side. So how the functions that correspond to those sections, how they are different. And I see that they are also different by multiplication by the same functions. Of course, this function should be pulled back because the function is the function lambda is initially defined on Q, and I want this function to be defined on L cross, so I just take the pullback. So if jets are the same, so if sections differ by multiplication by a function, that functions, homogeneous functions, also differ by the multiplication by the function, and the properties of this function. So the fact that it is 1 at some point has differential equal to 0 result that differentials of those functions are equal. Now, if I differentiate a function which is multiplied, I use Leibniz rule, I use the fact that this differential is 0, so this vanishes, and I use the fact that value of the function is 1, so only the differential survives, and I see that differentials of the function are the same. And then another thing that I want to observe is that, of course, I have a section on one side and the jet, and here I have a function on the bundle, so at each point, and I can take differential at each point of the fiber. But it happens that my action of the group just moves those differentials from one point to another along the function. So since I am just I speak for like 4 minutes longer than I should, so I will not explore it. It is written here, but I will not explore it, but this is just the message. I have a section, I have a function, and the differential of the homogeneous function and the differential of those functions in different places along the fiber are connected by my action. So if I divide by the action, I just have this jet represents the whole line of differentials, yeah? And this way I recognize an element of the jet as a class of as an orbit of air cross action along this bundle. Okay, so I suppose that's that for today. Next time, it means tomorrow, we will describe Hamiltonian vector fields in this language. Then we will see why the formula is like that. And then we will probably see, I think one application. Yeah, so that's all for today. Thank you.